It was just a daydream, calico and warm. No one's gonna save me, staring at the sun. Mama lost a baby, looking for the one. Got all bent and blinded, staring at the sun. Nightmares bound to follow over hill and dale today, but you're gonna swallow.
Hi guys, welcome back. So I have here with me Wojtek from he's a co-founder of NaniML, and he'll be talking to you about monitoring the flow for models deployed in production. So Wojtek, over to you. Thank you.
Cool. Thanks for the intro. So let's get started. And as you already know, today we're going to talk about how to monitor the models that are actually deployed to production. So let's get started with the first thing, which is the agenda. And on the agenda today, we have basically 4 items. First, we're going to talk about the main problems that you have to deal with once you deploy models to production. We're going to see what is the main problem and how it's not really that trivial to solve it. Then we're going to focus on the most typical way of solving that problem, and that problem you already have a bit of a spoiler here is model degradation. And we're going to talk about how we can solve that model degradation by looking at data drift signals, and then we're going to also discuss the issues with that approach and how it's actually not really solving the problem, unfortunately. Then we're going to talk about the real solution to the problem, and we're going to talk about how we can estimate the impact of data drift itself, not just whether the data drift is present, but what is the impact of that data drift on model performance. And we're going to build a bit of an intuition of how it's possible to do it in the absence of the target data or the ground truth data, so whether we can actually estimate performance without access to the targets. And then at the end, we're going to talk about a specific algorithm that we devised at NaniML and open sourced that allows you to estimate model performance without access to ground truth for classification models. And that algorithm was called CBPE, which stands for confidence-based performance estimation. We're not very creative with our names. So let's get started with the first part, which is post-deployment data science problems. And the main problem, as you see from Nature, there is a very nice paper called Temporal Quality Degradation in AI Models. And what they found is basically that almost all models degrade in time after you deploy them to production. We're going to talk about the causes of that in a minute, but just to see how serious that problem is, what they did is they trained, I think, a few thousand models on sets of data sets. They were both regression and classification data sets, and then they measured how the error of the model, I think they mostly used measures like F1 and ROKUC for classification and mean absolute error for regression, how that changes in time. And what you see, specifically, let's say at 365-day mark, is that the models on average, if we use mean as kind of a good representation of a typical model, then if we use median for that, we see that the models degrade around 20%. But if you get unlucky, you might get even a model that degrades significantly more. Let's say after a year, there were some models that already degraded more than 80%, which of course means that the models might go from providing a lot of business value to actually destroying business value or being actively harmful. So we need to know how well our models are performing. Once we deploy them to production, we cannot just rely on the test set data to say that the models are working fine. And here we basically go into the second problem, and the second problem is that we cannot just measure model performance using the targets, because the targets arrive after the damage is done. What do I mean by that? And again, there is a very simplified timeline when you see what happens with the data and the model kind of in time as you deploy the model to production. First, you get model inputs. Right after that, the model outputs some kind of prediction. This prediction is hopefully then used by the business to, for example, try to retain a customer or decide whether to give a loan or to buy more of certain good if you do demand prediction, et cetera, et cetera. Then based on that, you have a business impact, hopefully, for example, reduced default rate if you again deal with default prediction. And then after that business impact happens, a while later, you actually get the targets. So you will know whether that person actually defaulted on a loan or not. And if you're trying to predict, again, loans, let's say, a year ahead or 2 years ahead, you will only know that something is wrong after these labels start to come in. And that means that your model might be operating in a very suboptimal state. Basically, you'll be experiencing silent failure of a model when model is making bad predictions, but you don't know that it's happening for, let's say, a year or 2 years. So we need some kind of early warning signal to let us know that something might be going wrong with the model, that something is not as good as it used to be. So let's talk about what are the actual causes and what are the ways that we can try to get some kind of early warning signal that something has changed and that change might have a negative impact on model performance. The first thing, or the first kind of data drift that we're not going to be focusing on in this presentation too much is so-called concept drift. Concept drift is a conditional change of the target conditioned on the feature. And this is basically the concept that your supervised machine learning model is trying to learn when you train it. If that changes, then of course the model that you trained is no longer very relevant, and your model is going to make much more mistakes than it used to. So this is something that, of course, we'd like to be able to spot early on, but as you see in the definition right here, you have the target here. So if you don't have the targets, you cannot really do that, or it's, as far as we know right now, given the current state of literature and technology, impossible to do it without access to targets. So nothing we can do about it. We have to focus on the second and luckily much more prevalent type of data drift, which is called covariate shift. And covariate shift is just the change in the joint model input distribution, so change in how all the features are distributed together. And this is something that we absolutely can detect early on. We can detect it as soon as we get model input, so we can detect it not only before we get business impact, but even before the model makes prediction. Because you see here, we only have the features. So we're going to be focusing on, when it comes to both data drift detection techniques and then later on the performance estimation techniques, we're going to be focusing only on the covariate shift. Now, let's talk about how we can try to detect this covariate shift, and we're going to be focusing on high-level approaches only, and whether this actually works in trying to estimate model performance or trying to get some kind of early warning signal that something is wrong. So I'm going to start already with the problems, because we don't, unfortunately, have that much time, and I cannot go too much into details about the specific methods. But suffice to say, we're going to basically look at methods that look at the distribution at the test set data. They look at the distribution at the current batch of predictions, and they compare them in some way. But if we do that, and we say, let's say, 300 features, 400 features, hundreds, or sometimes in some use cases even 1,000 features, what's going to happen if we use statistical methods? We're going to get a lot of false positives just from statistical perspectives. If you use your p-value to determine whether there is a significant difference in the distributions between your test set and your current batch of predictions, and you stick with traditional 5%, and you have, let's say, 200 features, you're going to get 10 false positives just from statistical perspective every time you run those tests. So they're bound to happen, and you're going to be basically just flooded with false positives. But maybe you have a smarter way of looking at it. You don't focus on p-values, you focus on something else. You focus on the magnitude. Maybe you use distance-based metrics such as Jensen-Shannon distance, and you try to compare the distribution. And this is something that will give you meaningful changes in data distribution. But it still doesn't mean that you don't have false alerts, because the models are robust to changes in data distribution. When you train a model, the model is likely to perform reasonably well everywhere it has been trained. So if the data drifts from one region that was reasonably well represented in your training set to another region that was also reasonably well represented in the training set, and the performance in both those regions was similar in the training set, then your performance in production, even though you experience significant covariate shift, is still going to be good. So that's another reason why you're going to have a lot of false positives. And then finally, drift in the relationship between features is not captured by the univariate drift methods. So if you have a picture like here, when you basically have two features, and for some reason, maybe in data processing, those features were swapped and then rotated 90 degrees, And you see that basically the distribution in week 10 was as such, and the distribution in week 16 was as follows here, the red one. What you will see from univariate perspective is basically no change. And if you see features that are strongly correlated, you will see that quite often there's absolutely no errors here. But if you look at the actual distribution, it's going to be completely different. And that means that your model is probably not consuming this data as it should. It's an actual data quality issue because the features were swapped. But your univariate drift detection methods did not capture that. So that is something that we can solve with multivariate drift methods that we're not going to be focusing on, again, too much this time because we don't have 2 hours. But the first two will not be really solved with multivariate drift methods, so we need something else. And to kind of showcase that this is indeed the case and that all these problems are actually real, we looked at a bunch of data sets from US folk tables data set, which is basically all data about American population that you can publicly get. And in total, we got, I think, 600 data sets across different tasks. And we trained a group of models. It's mostly gradient boosting, but we also trained different models to make sure we have good coverage across different models. And we plotted the actual realized ROC AUC, or ROC if you prefer, of those models over time. We chunked that data into, if I remember correctly, 2,000 data points in each chunk of data. And we plotted this time series. And basically what we're trying to do to get this early warning signal is we're trying to get an information about the behavior of that time series in time before we get the targets. So at inference time, we get information about model input distribution, and we're trying to predict what's going to be the ROC or ROC AUC of that batch of predictions. And we see on the test set, which is here in blue, everything is fine. The model performance is quite stable with a bit of noise in it, around 91. So it's a very good model. And then at some point, there is a strong data quality issue that actually happened in the data. There was something wrong with data collection, and the model just completely collapsed. And then it recovered, but it did not recover fully. So we have two kinds of issues and two kinds of drops in performance that we generally observe in real-world data. You sometimes have these huge downward spikes that recover that are mostly related to data quality, and you also have this persistent data degradation that's significant, performance degradation that's significant, which is what we observe here, where the baseline that the model performance recovers to is not exactly the same as the baseline it used to be on. Now, what did we do? We basically looked at all those data drift signals, mostly from univariate perspective, but we also did some multivariate experiments. And here what you see, for example, is that we used the Jensen-Shannon distance for both categorical and continuous features, and we trained the logistic regression model to try to estimate ROC AUC based on that. And we trained it on the test set to make sure that everything is fine in terms of the model performance, that the model performance is actually representative of the expected model performance, so we cannot use the train set to do that. We did it on the test set that was not seen by the model beforehand. And we see that, unfortunately, if we train a simple model, we get a bit of a noise. If we train a more powerful model, such as random forest, we get basically a straight line, because the model learns that there is no information there. Sometimes the models were trained to be actually overly sensitive, and anytime there is an issue, it just craters down. I think it goes to like 0.5, and it says that now the model is completely fucked and nothing works. So just based on that, on this specific example, we see that there's issues. Now, I'm going to give you a bit of a preview for our best method right now for estimating model performance. And we see that it actually is able to detect both the spike and persistent model drop. How did we do it? In a second, right now, let's just look at the summary of the performance on all those data sets that we evaluated. So I think, again, it was around 600 data sets. And we see the first part is the test set, so we just assume that the model performance does not change. We already know that this is a bad benchmark because the model performance does degrade, but we need to know how much and when does it degrade. So we're going to compare everything against using test set as the benchmark predictor. It's basically a naive prediction when we assume everything is the same. And then we have two methods that we developed. We have CBPE, which is the simpler method, and we measured the mean absolute error of the estimation of the ROC AUC. And we see that both of those do beat the test set, and if we try to use any of the univariate drift methods, they're actually significantly worse than the test set because they either get the completely random noise, which is going to be slightly worse on average than just assuming everything is flat, or we get these overly sensitive drops in model performance that either give us false positives or sometimes find something, but they also find everything. So it's kind of the broken clock that's right twice a day. So we cannot use that. What can we do then to actually estimate model performance? You already saw a bit that there are methods that actually work. Let's talk about how can we actually estimate model performance without access to the target data. And to do that, I'm going to start by building an intuition. And the intuition is as follows. Imagine that we have the simplest possible regression model. This regression model uses one feature X, predicts continuous feature Y, and it's just a straight line. I created this super simple synthetic data set. We fit the bias optimal classifier, the best possible classifier that uses all the information in the data to make inference about the actual target, about the target Y. And kind of the naive intuition that I also used to have is that if you use all the information in the data to make some kind of inference about the target, then you can't say anything about its performance on top of that. Because if you could just incorporate that information into your model, and the model would be better. Turns out that this is actually not true, and these problems are orthogonal. One of them is basically predicting the target. Another one is, in essence, uncertainty quantification of the model itself, of the predictions. So these issues are surprisingly orthogonal. And I think this plot here shows it quite nicely, is that what we see is that we have a perfect model. And now, just looking at this, can you say in which regions in the model input space the model is going to have higher performance or lower performance? The answer is quite obviously that if we are here, the model is going to have lower MSE, MAE, whatever metric you use, because the level of noise here is much lower than the level of noise here. Here, we have much more noise in the data. There is something that is maybe additional unseen feature that we don't have access to that increases this standard deviation of the data points here. And to kind of prove the point, I calculated the rolling mean error when I took the window size of 100 across the feature X, and we see that indeed for low values of feature X, the model error is much higher. So just based on where the data is in the model input space, we can already say something about its expected level of performance because it's directly related to the level of noise related to the concept that we're trying to learn, so the mapping from the model inputs to the targets. So we can actually say that the model here is going to perform much worse than the model would perform if the data comes from that region. And then we can use that intuition together with covariate shift to say something about the expected model performance. Now, let's expand to more dimensions. Let's look at and keep on building that intuition now in 2D. And also, let's switch to classification, because why not? So what you see here is typical XOR problem when we have, you know what XOR problem is. And what we have here is basically we train a model, nonlinear SVM, because why not? And we see that we have this predicted probability. And maybe instead of trying to train a full new model to try to estimate this uncertainty, we can actually leverage that predicted probability. And turns out we can. The way we do it is we're going to turn these predicted probabilities into some kind of measure of uncertainty. And this measure of uncertainty here, in a very non-scientific way, I called confidence, which has nothing to do with confidence intervals or anything like that. So, don't get too excited about that if your background is statistics. But basically, confidence here means that how close the prediction is to either 0 or to 1. You have a very quick formula here, which is a bit trivial. And just to compare those two, no, there's no comparison slide. So what you basically see is that if there is a lot of predictions that are very confidently predicting 1 or 0, we're going to have high confidence here and here. And if we're getting close to a class boundary, then our confidence will drop. And we can expect the model to perform worse if we have a lot of data close to the class boundary. It's obvious when you think about it, but it's actually a very important insight that will allow us to estimate model performance without access to ground truth. Now, how do we actually take that insight and turn it into a specific number that can tell us that our ROC AUC dropped by 5%? We're going to start by creating the estimated confusion matrix. So even though we don't have the targets, we're going to try to fill in confusion matrix with some kind of numbers. I'm going to use binary classification here because it's easier, but the same approach works for, let's say, if you have 1,000 classes. It's just impossible to plot here. And the way we're going to do it is we're going to go prediction by prediction, row by row. Of course, in practice, it's vectorized, but let's focus on simple explanation here. And we're going to try to say something based on the information we already have at the inference time. First thing we know is that the first prediction turns out to be positive. What can we say about the confusion matrix? Well, it's not negative. So we can already fill in negative. False negative and true negative are for sure 0, because we already know that the classifier returned a positive prediction. So far, so good. Now, we have the second part, which is, again, this key insight, and it's slightly more contentious, which is we can use the predicted probability as a way to say that we can actually fill in something here in expectation, assuming large enough data sample, and if this predicted probability conforms to the Frequentis definition of probability. So if we have, let's say, 10 million data points that all return 0.7, then we would expect 7 million of those to actually turn out to be positive. So we can say that then, in expectation, if this is an actual probability, we can fill in 0.7 in the true positive cell and 0.3, the remainder, in the false positive cell. And this is really the key insight. This allows us to get this. And once we have this instance-level confusion matrix, we can get lots of instances, just sum them up, and then we can compute any metric we want based on that. Second prediction, let's say we get a 0 this time, predicted probability 0.4. We're just going to fill it in the negative part of the confusion matrix. Then we can take any metric we want. In this time, it's accuracy because it's the simplest, and we're just going to use our well-known definition of accuracy. We're going to take that, and we have our estimated accuracy for these two predictions. Of course, for these two predictions, the expectations don't really matter much. They don't mean anything because we're going to have a lot of noise, and we cannot have really partial confusion matrix elements. But if you get 1,000 predictions, 2,000 predictions, you actually end up getting quite good estimations here. But there is a problem. And the problem here is that this number is not a probability. And this might be already known to you if you know of probability calibration. But for those of you who are not familiar with the term, I'm going to briefly introduce calibration and what it is and how it helps us turn those numbers, the 0.7, which is a number that is called predicted probability, but actually has very little to do with actual probability. So what you see here is a so-called calibration curve or reliability curve. They're all implemented in scikit-learn, so you can talk to the probable guy about it. But to give you a very brief description, the way we do it is we're going to bunch up, or we're going to bin all the predictions on our test set into, let's say, 10 bins. Each of the bins is going to be between 0 and 0.1, 0.1 and 0.2, etc. And then we're going to measure the mean predicted probability in that bin. And we're also going to measure what is the actual fraction of positives that we observed in that bin. And if the predicted probability actually conforms to the Frequentis definition of probability, what we expect to see is this straight dotted line, because then they match. The mean predicted probability matches the actual observed fraction of positives. What you see is that for almost all models, everything that is not logistic regression, also that includes any kind of deep learning algorithm that you do on non-tabular data, you're going to get mostly this S-shaped curve. So you cannot trust those predictions at all, the predicted probabilities, to represent probability. So what we're going to do is we're going to calibrate them. Calibration is simply a 1D regression task, where we're going to take the classifier's predicted probability, and we're going to map it to the expected fraction of positives that we have. This is normally done with isotonic regression, but interestingly, we realized that you can also use LGBM, and it gives better results, because LGBM always gives better results, apparently. And that's it. Then we have a straight line, and we can trust it. So then, instead of using the actual predicted probabilities, we're going to use this calibrated predictive probability. And in NumML, this is all done behind the scenes, so you don't actually have to have calibrated predictive probabilities if you don't want to for some reason. Maybe it's you have a regulated industry and you cannot do it, or you're just too lazy to do it and it happens automatically. And then you can use those, and then you actually have nice guarantees that you get good estimated performance. The problem is that it works for the entire reference set, so for our entire test set at once. We only get those guarantees if we look at all of the data at once, and it only works for the covariate distribution that we're observing on the reference set, which, of course, is a bit of a problem because what we're trying to do is we're trying to see what is the impact of covariate shift on model performance. But we're assuming here that there's no covariate shift. Turns out that we can violate this assumption, and then empirically it works quite well up to a certain point. To give you an example here of a very interesting false negative for using data drift signals as a way to predict, to estimate performance. We have multivariate drift detection that uses PCA reconstruction error. Again, no time to go into details here. It's a quite robust way of detecting drift at the entire data set at once. And we see that basically the performance is stable. We see that our drift metric is quite stable here, but we still see a very strong drop in performance, and accuracy is more than 15 percentage points. And we are able to estimate that with CBPE. If we go into places where we have actually strong data drift, then CBPE is going to be directionally correct, but it's going to mismatch the magnitude a bit. And for that, we developed an algorithm that actually guarantees calibration, even for basically arbitrary data distribution. But again, we don't have time. This algorithm is called PAPE, and you can look at our documentation for that. Or talk to me later, or ask me the question. And now, just to summarize, what we hopefully learned here is that, first of all, model performance deteriorates in time. This is mostly due to covariate shift and sometimes due to concept drift. Targets do not arrive after the damage is done, after we've lost, or the company has lost a lot of money. So we have to get some kind of early warning signal. Then, unfortunately, data drift signals by themselves cannot be used as a proxy for model performance degradation, so just whether we have some kind of silent model failure. But we can quantify the impact of covariate shift on model performance without access to the target data to ground truth to labels. And we can do that for classification tasks with either CBPE or PAPE, which is this algorithm that also takes into account strong covariate shifts. And for regression tasks, we have another algorithm called direct loss estimation. And what it does, it trains a model that directly estimates the loss on every data point, and it uses the exact same thing as CBPE, but for regression. And we actually can get good estimates of any model metric that we want. To be a bit more specific here, if you want to delve deeper later on into our what we have to offer, we have performance estimation, so we can, without access to targets, estimate model performance for classification and for regression. We also have a way to detect concept drift, which is quite cool because it gives you a very strong signal to retrain your model. Your performance might drop, but if it drops due to pure covariate shift, then your retraining will actually not fix it. But if it drops due to concept drift, then you know that by retraining your model, you're going to capture this new and updated concept, and you're going to be able to actually improve your model performance. Then you can also estimate any metric. So far, I was focusing on typical metrics like F1, etc., but there's no reason why you couldn't construct any metric you want that's not necessarily even based on a single confusion matrix, so you can use something also like precision recall curve and get the area under the precision recall curve. Or you can use how much money your model is making if you can quantify the value of each false positive that you make and false negative that you make. You can also estimate that. And then finally, on our cloud platform, we have alerts, so if something goes wrong, then you know on Slack that it went wrong. And integrations and all that engineering is handled. I have no clue about that because I'm a research data scientist, but if you're like me, then you also don't want to know about it and you don't want to be bothered, so it's handled. And that's it. Thanks for listening.
Okay, thank you, Wojtek. So we have some time for questions.
Thanks a lot for a nice talk. I was wondering if you've detected with the NannyML package that there is covariate drift. Does the package also advise on what datasets subset to retrain? Maybe it's discovered data drift somewhere. Does it provide like a cutoff and say, if you're going to retrain a model, use this sort of this part of all the data to train?
Yeah, that's a very good question. And I'm going to do another NannyML cloud insert here, which is, it's not in the open source, but in the cloud package, we have concept drift detection that, again, tells you about when to retrain your model. And what you can do there, we also have segmentation. So you can look at the segments of your data, and you can see in which segments you have significant concept drift. And then you can focus your retraining efforts on that particular segment. What I know is that in a lot of retail data, and if you do demand forecasting for, like, let's say, 1,000 different products, you normally have different models for each of those products. So instead of just blindly retraining them all, you would retrain only the models that work on segments that have significant concept drift. So if you want to focus on retraining and being smart about retraining, then concept drift is the thing. But science is open, so you can also implement it yourself if you want, or with the cloud.
Cool, thanks.
Hello, I have a question about calibration. I don't know if your package offers something about that, but how do you access your calibration? Only looking at the plot, or you also have some metrics for that?
Yeah, so when it comes to calibration, right now we have kind of two default methods that we know that they work in kind of AutoML way, because generally we cannot see your data, so everything that happens inside your environment. So we need to have algorithms that work quite well with AutoML. And we have isotonic regression and LGBM calibration. And the way we see if they work, we're using so-called expected calibration error when we do cross-validation on your test set, and then we measure the calibration error on out-of-fault calibration, which is basically just looking at it from a regression perspective and seeing if this curve is actually aligned to be a straight line. And then you can also access the actual calibrated probabilities directly. But if you just want to calibrate your models, then I would use scikit-learn. If you want to use this calibrated outputs to the model monitoring, then use NannyML.
Hi. Thanks for interesting talk. If I understand correctly, your model is a meta model, so you use it's a supervised setting when you use the targets in the past to train your model, correctly? Or it's unsupervised setting?
So it is supervised, but we don't use so we use the targets to calibrate. We don't use the targets for actually directly estimating performance, but then we use these calibrated probabilities to do this trick when we can fill in the confusion matrix. So we use them indirectly. It is a supervised model.
Yeah, yeah. So does then your model also drift?
Yes,
right?
It can. That's a very good question, and it's the question of who watches the watchman. If we see that, yes, the model is drifting, maybe our model is also drifting, and this might absolutely happen. And then the logical conclusion is to build this infinite tower of models that watch each other. And of course, I can already see that it doesn't make sense. So from empirical perspective, what we see is that our model is basically modeling the uncertainty or the loss landscape of the underlying model. And this loss landscape tends to be much more persistent than the underlying model. So just strictly empirically, we see that our models can drift, drift very rarely. And interesting thing is that you might experience concept drift of the underlying model, but the actual uncertainty landscape still doesn't change.
Okay, we have time for last question. So,
hi, thanks for the nice talk indeed. I was wondering about detecting covariate drift when you have seasonal inputs. So, for example, weather is one. There's many, obviously. So obviously, you have to choose some degree of reference period. But yeah, I wonder if you have any best practices or guidelines with regards to that.
Yeah, that's another good question. So when it comes to seasonality, that's another reason why you shouldn't use data drift signals to estimate model performance, because you're just going to get, if it's not the average, you're going to get drift, and that will give you false positive. But if you focus on performance, then you're just going to get performance for that particular place in time. which is something that you want to know even if it's seasonal. If you get bad at predicting ice cream sales in the summer, then you'd like to know it even if it's normal. We also have on the roadmap deseasonalizing everything, so then you can get like all your outputs taking into seasonality into account. So if there's season when it's bad, then you don't see it and it doesn't trigger alerts. But we're prioritizing that against other stuff, so it's not there yet.
All right, thanks.
All right, thank you guys. As a token of appreciation, thank you for being here.
That is
That's
cool.
great.
Thank you.
Thank you guys.
You wear those shoes and I will wear that dress. Oh.